So I've given you a vector on the x and y axis here, and let's say it has initial point at P and terminal point at point Q. And we're given that from the graph that the initial point is at 1, 2, and the terminal point is at 3, 1. So knowing our knowledge from the previous video, we know that the component form of vector PQ is given by 3 minus 1, 1 minus 2, and that's given as 2, minus 1, which is correct because we could go 1, 2, and then down by 1. The negative implies we're going in the negative y direction. So this would be our component form for vector PQ. Now let's do a slightly different problem. Let's say I give you the vector u with initial point P at 3, 2, and terminal point at 5, 6. And I also give you another vector, call it v, and v has initial point at 1, 4, and terminal point q at 3, 8. And I want you to show that these vectors, u and v, are equivalent. So we're going to show this statement here. Give that a try. Well, to show that two vectors are equivalent, we have to show that their magnitude and their direction are the same things. So let's start by showing that their magnitudes are equivalent. The way that we have to do this first is we have to put them both into component form. So for u, that would be 5 minus 3, which is a 2, and then 6 minus 2 gives us a 4, and then v, sorry. The component form for v would be 2, 4. So looking at this right now, we see that u and v both have identical component forms. So we could go ahead and actually use the Pythagorean theorem if we want, but it's both going to be the same numbers. We see that the magnitude of u is given by the square root of 2 squared plus 4 squared, which is going to be 4 plus 16, which is the square root of 20. And we get the same thing for the magnitude of v. We don't even have to do it because they're the same exact numbers. So we've already shown that they have the same magnitude, the same length of the vectors. And you could say 5 rad 2 or rad 20. But yeah, so they have the same magnitude. And now for direction, we could, if you want, we could do this two ways. We could use, we could find an angle. We know that if we were to draw the vectors out, let me move this down here, sorry. Oh. I'm pretty new to this drawing software. Give me a minute, I'm sorry. If we were to draw these vectors out, well, what's going on here? There we go. If we were to draw them out, we would see that they would go 2 on the x-axis and 4 over here. This is not the scale, I apologize. But if we were to find this angle here, this specifies the direction. So we would find that tan theta is equal to 4 over 2, and therefore arctan of 4 over 2 will give us theta. And we get the same theta for both cases. We don't even have to calculate it. But yeah, we've essentially shown just by finding the component form, just because they have identical component form, they must be identical vectors. So now I'm giving you two vectors, once again, one vector, sorry. We'll call it b. And I would like for you to find the component form, given that the initial point is at 2, 0, and the terminal point q is at 5, comma 5. So go ahead, find the component form of vector b. Well, here we would just do 5 minus 2, comma 5 minus 0, giving us a component form of 3, comma 5. That's the correct answer. Now this one's a little bit more challenging, just a little extension of what we've learned so far. So I'm giving you a vector, -1, comma 3 in component form, and I'm given that the initial point is 4, comma 2. 4, comma 2, I apologize. The initial point is 4, comma 2. So now I would like for you to find for me the terminal point, call it x, comma y. We don't know what this is, but we could solve for it. So go ahead. Well, I know that to find the x component in the component form, I would have to do x minus 4. So x minus 4 is equal to minus 1. So therefore, x must be equal to positive 4 minus 1, which is going to give us 3. And similarly, I know that the y component, 3, is given by y minus 2. So y minus 2 equals 3. Y must be 5. So we know that our terminal point must be 3, comma 5. And we can check our answers because 3 minus 4 is indeed a -1, and 5 minus 2 is indeed a positive 3. So this must be our final point, terminal point. Let's do one more of those examples because that's usually a very frequent test question. So once again, you're giving some vector v, 4, comma -9, and we're given that the initial point is 5, comma 3. And we want to find the terminal point x, comma y. So go ahead. Well, I know that x minus 5 is equal to 4. So x must equal 9. And I know that y minus 3 must be a -9. So therefore, y must be equal to 3 minus 9, which is a -6. So q would have the point 9, comma -6, and we can check our answers real quick. 9 minus 5 is indeed a 4, and -6 minus 3 is indeed a -9. So this must be our terminal point. So now I have the vector A, and we're giving this in a different notation, I and j notation. And given this, I want you to find the magnitude of vector A. So to do this, we just have to use the Pythagorean theorem. It's just the square root of 3 squared plus 4 squared, which is going to give us square root of 9 plus 16, and which gives you the square root of 25, which is 5. You could also just notice that this is a Pythagorean triple, and the hypotenuse must be 5 because 3, 4, 5. So here's another vector. Let's say it's 3, comma 5. And this is v. I want you to find for me the vector 2v. Well, to do this, we would just have to stick a 2 over here. So I would have to find 2 times the vector 3, 5, which is going to be 2 times 3, comma 2 times 5, which is, of course, 6, comma 10. All we have to do is just scale the insides by a scalar multiple of 2. So once again, let's just check this. 6 divided by 3 is a 2. 10 divided by 5 is indeed a 2. So this must be 2v. So here's two more vectors. Call them 4, 9, and 2, minus 5. And I would like for you to find u plus v. To do this, we just have to add the individual x and y components, which would be 4 plus 2, 9 minus 5, which gives us a vector sum of 6, 4. So if you were to imagine these as like forces, and we want to find the resultant force on a body, we just add the forces up, and this would give us our resultant force. That's what u plus v is. Let's do one more of these examples. Let's say, in this case, u is negative 3, minus 8, and v is 8, 7. Now I would like for you to find 2u plus 5v. Well, first we'd have to scale this by a factor of 2. So that would be 2 times negative 3, minus 8, plus 5 times 8, 7. All I'm doing is just sticking a 5, a scalar multiple of 5 over here, and a scalar multiple of 2 over here. So this would, of course, give you negative 6 minus 16 plus 40, 7. All I'm doing is just multiplying the insides by the scalar on the outside. Negative 6, negative 18, 40, 35. I think I was talking when I was doing that calculation. So now, all we have to do is just add the insides. This gives us a grand total vector of 34, and 5 minus 16, which gives you, what is that, 19? So 34, 19. Now this is a very important thing that you have to be able to understand if you want to study multivariable calculus. So once again, of course, we're given some vector. And let's say in this case, it's 3, 12. Now I would like for you to find a unit vector, a vector of magnitude 1, in the same direction as vector v. So to do this, all we have to do is first find the magnitude of vector v, which in this case is 3 squared plus 12 squared, which is the square root of 9 plus 144, which is the square root of 153. And to find a unit vector in the direction of v, we would have to divide v by the magnitude of v. So now it would be 1 over the square root of 153 times 3, 12. And there's not much that you can do to simplify this. If you want, you can bring the scalar inside. But sure enough, you were to try this out in a calculator and find that the square root of 3 over the square root of 153 squared plus 12 over the square root of 153 squared. This quantity will, of course, come out to 1 because this is a unit vector in the direction of v. So this would be a good way to check this answer on a test. And this would be a perfectly good answer, but If you were to simplify, just make sure to simplify. So let's do a little bit of a challenge question here. Say I give you the function f of x is equal to x squared, and I want you to find for me a vector that is tangent to the graph of x squared, a unit vector, sorry. Unit vector that is tangent to the graph at 3, 9. Well, first, to do this, first thing I would want to do is what's the slope at 3, 9? So we can take the derivative. F prime of x would of course be 2x. And if I want to find the slope at 3, 9, I'd have to find f prime of 3. So that would be 2 times 3, which gives us a slope of 6. So if I was to like kind of sketch the graph, I know that at 3 here, if you were to have any kind of vector here, I know that the slope, or the change in y or the change in x, would be a 6. So if this was 1 here, and this was a 6, then that would describe some kind of vector going through the point 3, 9. So let's call it u, actually let's call it v. We'll call the unit vector u. So I know that from the slope alone, it would be, not 6, 1, 1, 6. V hat would be 1, 6. And now I want to find a unit vector for vector v. So I'd have to find the magnitude of v, which is the square root of 1 plus 36, the square root of 37, which is 1 over the square root of 37 times 1, 6. And you can put this into a graphing software, and this would be a unit vector that is tangent to the graph of x squared at the point 3, 9.